Hello everyone and welcome to Applied Engineering channel. Here we discuss the innovative ideas and concepts regarding thermodynamics. So this is part 2 of my PhD defense and chapter 2. So in this chapter I will discuss in detail the methodologies and the results of my research. The research phase slides are arranged as per my research journey and are divided into three different phases. So in this part, I will discuss the first phase of my research journey, which includes my work on energy, exergy, and environmental, that is 3E screening of low GWP refrigerant pairs for sustainable cooling. When I started, there were very few studies that explored the next generation refrigerants for ultra low temperature refrigeration, and there was absence of comprehensive 3E analysis which incorporate the life cycle climate performance, that is LCCP, for cascade refrigeration systems. Also, R1132A was used for the first time, and its Spang-Robinson equation of states was used with the help of our collaboration with NextRip, which is the main novelty of our work. R23 and R404A were used as a reference pair for comparison in this study. For the high temperature cycle and low temperature cycle, different low GWP refrigerants like HFC, hydrocarbons, and natural refrigerants were selected. Recently, ASHRAE approved zeotropic mixtures like R455A, R454C, R459B, along with R1132A were considered for the first time in this study. The refrigerant filtering were done based on the thermodynamic parameters as well as their GWP values. The thermodynamic model starts with the selection of refrigerants after the input and design parameters like reference temperature, pressure, duty, condenser and evaporator temperature, superheating, subcooling, and compressor efficiencies. RefProp 10 is used to calculate the thermodynamic properties at these state points, but the cascade condenser temperature has to be fixed first to get all the state points of the cycle. For that, iteration is being done in which the cascade condenser temperature is increased and an optimum point is finded out where the system has maximum COP. To get only the practical feasible results, boundary conditions are then applied. These boundary conditions includes the compression ratio of both compressor cycle to be less than 15. Compressor discharge temperature should be less than 150 degrees Celsius, and the evaporator and heat exchangers pressure should be greater than zero point 0.5 bar absolute. After that, the main parameters like work, COP, exergy destruction, exergy efficiency were evaluated with changing in the evaporator temperature with a step of 5 degrees Celsius, and tables and plots were generated. This thermodynamic model is verified with the experimental and theoretical models, and you can see that the deviation is not more than 10%. So the present model is a reliable simulation model that can be utilized for performing the first and second law analysis on different refrigerant pairs. It was validated with the experimental work of Dopazzo and Fernandez, and it was also validated with the theoretical model of Lee. So, in the first phase of my research, we observed how the main performance metrics like COP, exergy efficiency, varies as evaporator temperature increases from minus 30 to minus 80 degrees Celsius. The following plots shows how the COP of the cascade system varies with the change in the evaporator temperature. The COP of the system increases when the evaporator temperature increases because it decreases the temperature lift and hence the compressor work. In the plots we can see that there are mainly two groups of pairs, one which is performing better than the baseline pair and the other group which is performing worse than the baseline pair. The main points which were observed were that the natural and the pure refrigerants like R170, R161 and R290 performed better than their counterpart HFC refrigerants like R454C, 459B and 455A due to their better thermodynamic properties. Exergy efficiency measures how effectively the system converts available energy into useful refrigeration, considering both the quantity and the quality of energy. These are the plots representing how the evaporator temperature and exergy efficiency correlates, increasing the evaporator temperature from minus 80 to minus 30 degrees Celsius of different refrigerants like R23 with HTC, R1132A with all HTC, R41 with all HTC, and so on. Exergy efficiency increases with evaporator temperature and peaks at minus 50 degrees Celsius to minus 45 degrees Celsius and then decreases. This is because it captures the irreversibilities across all the system components like compressors, evaporator, condenser, cascade heat exchanger, and expansion valves, and incorporating all these irreversibilities as the evaporator temperature varies. So for the refrigerant comparison, the results were same as the natural and the pure refrigerants are performing better than their counterpart HFC refrigerants. To further dig deeper, we performed the component-wise exergy destruction analysis of the selected top performance pairs, which were R23 161, 1132A 161, 41 161, 116 161, and so on. So 161 was the best performing high temperature cycle refrigerant. Also 1234YF is taken because it has less flammability of A to L, whereas R161 has the flammability of A3 category, and they were compared with R23 R404A as a baseline. So why this component wise exergy destruction analysis was done? It is performed to see which components are actually generating more exergy destruction and they need modification in their design. This resulted that the compressor and the condenser of the cascade refrigeration system were involved in more than 57% of the exergy destruction, that is energy wastage. And this concluded that these two components need future design modification for an efficient cascade refrigeration system. The component which contributed minorly was evaporator. So, for the environmental analysis, LCCP was performed. LCCP stands for Life Cycle Climate Performance and it consists of direct emission as well as indirect emissions. In the direct emissions, it counts the refrigerant leakage as well as atmospheric degradation of refrigerants. In the indirect emission, it accommodates the energy consumption emissions and the material manufacturing emissions, refrigerant manufacturing emissions, and the material and refrigerant recycling emissions. So LCCP is the sum of all the direct emissions and indirect emissions, and it is called a cradle to grave CO2 emission analysis. These are the formulas for calculating the direct and indirect emissions. Following graph represents the LCCP results, and we can see that only the high GWP refrigerants are producing the direct emissions. The key findings were that R116 and 161 shows the highest CO2 emissions, whereas R170 and 161 exhibits the lowest CO2 emissions. And when we switch from R23 and 404A to R170 161, we have almost 40% reduction in the CO2 emission. So the key findings were that R170 and 161 is the recommended refrigerant pair. But if we want some pair which have less flammability, then we can also use R1132A and R1234YF, which also has a comparable performance. For the environmental impact, R170 and 161 has the least environmental impact, and we can see it has 40% reduction in CO2 emission. So in this phase, I had two publications, one in the IJR International Journal of Refrigeration and one in a conference Cheshire. So this was the first phase of my research. If you have any question, please ask in the comment box. I would love to answer your questions. Please like, share and subscribe my channel if you like my videos and updates. That is the only way of supporting and motivating me. Thank you very much.